to hit recording. Well, too bad on the material before, but I will upload the notes from now on. So if you miss something, you can always go back to look at the notes. Right? Let's continue. It's -6, right? The dot product here is 1 times -2, so which is -2, plus -1 times 2, which is also -2, and then 1 times 1 becomes 1. All right. So the number here is -2 plus -2, which is -4, plus 1 is -3. So you have -6 plus -3 becomes -9. And again, these two numbers are the same, right? Because these are the properties of dot product. Right? Does it make sense?
Professor, could you like show a visual representation? Like, let's say you have two vectors on a graph. Like, how would that, like, what is the dot product result? You know,
All
like
right.
on a
Yeah,
graph.
we will get to
'Cause
that. All right.
okay,
The interpretation on dot products,
yes,
application on dot products. All right. We'll get to
yeah.
that. Yes.
Okay, great, thank you.
Yeah. Any questions so far? Okay. All right. So one of the interpretation on dot products. So what is the interpretation? Right. Well, geometrically. For dot products is that when you look at two vectors in the Euclidean spaces, these two vectors can be represented by two arrows with this the origin as the starting point, right? Oh, by the way, the video on yesterday, it seems like the cloud storage for Zoom in Hunter is really limited, and I can put up all recordings on Zoom on the cloud that that would blows up the storage. So instead, I would have a local storage first, and then I would upload this video on YouTube, and then I would post the link of this YouTube video to Blackboard, right? So you can view it afterwards. So it's the processing would be a little bit longer than just post the cloud recording link to the Blackboard, right? This like a 3-second thing. Right, so it would take a little bit more time than usual, but it should be there. The link for yesterday's video is already up. Right, you can check Blackboard. Go to course material. There is a folder called links on recording, and it will be there. Right? Any questions on this topic? Okay, so when you go back to the course material here, so when you look at these two vectors, right, you can see that they can form a parallelogram with these two vectors as edges. Okay, so the dot product represents well, really not the dot product value itself, is the absolute value of this dot product actually represents the area of this parallelogram. So when you look at this parallelogram, right, the area of this parallelogram is actually the same as the absolute value of this dot product. Okay, and so what is the negative dot product mean, and what is the positive dot product mean? So when you have positive dot product, it just means that these two vectors, the angle between these two vectors, right, are a acute angles, right? The angle is less than 90 degrees. And when you have a negative dot product, it just means that the angle is more than 90 degrees. So the sign tells you about the angle, but the actual value represents the area of this parallelogram. All right. So this gives you, well, leads you to the second application, is the angle between two vectors. Right. So not only the sign.
Professor, can you repeat the part where you said it's less than 90 degrees, and what do you say by that? Something negative or positive? What?
Right, we will get to that where we would do it more thoroughly in the second.
Okay.
Right, right. But so the first one, right? We only talk about the absolute value, right? The sign doesn't matter. It can be positive, negative, or zero, right? And wait, hold on a second. Let me sketch that. Hold on a second. Well, I think I made a mistake here. 1 second. Doesn't make sense. No. I think I make a mistake. The scratch this part. the area of the parallelogram is not determined by the dot product, it's actually determined by the cross product. I'm so sorry about that. The dot product only deals with the angle between the two vectors. So sorry about that. All right. So the angle between two vectors, all right. Yes. If one way to look at that is, if we have two vectors pointing at the same direction, the number is not zero, but the parallelogram formed by these two vectors is just a zero, because you can't form a parallelogram with two edges pointing in the same direction. So, right. So the dot product only talks about the angle between two vectors. All right. So if the vectors have acute angle, right? Basically, the two vectors form an angle less than 90 degrees, right? The dot product is always positive, and if the vectors form a angle greater than 90 degrees, on the other hand, you have a dot product less than zero. All right. So, for example, if the v here, right, in R2, we have only like XY plane to talk about. All right, that would be a little bit easier. This is 1 and 2, and the W is 4, 0, for example. The dot product between V and W is 1 times 4, 2 times 0. So the result is 4. On the other hand, if we have V is 1 minus 1, sorry, minus 1, 2, and the W remains 4, 0, then V dot W is minus 1 times 4, which is minus 4, plus 2 times 0, which is 0. So the result is minus 4. This is one of the examples on, less than 90 degrees, more than 90 degrees. Okay, so in general, the angle of between two vectors can be accurately determined by the dot products. Well, so the formula or the relationship between angles and dot products is determined by the formula here. The cosine of the angle between two vectors is the same as the dot products. The two dot product divided by the length of vector V and the length of W, vector W. All right. So, well, we haven't talked about the length here, but in general, the length is always a positive number, right? When we talk about length, same thing here. So the sign is really determined by this dot product, because your denominator is always positive, right? So if you have a negative dot product, the cosine here is negative. If you have a positive here, the cosine is also positive here, right? And the cosine, well, because the angle is between two vectors, is always between 0 and 180, right? If you have more than 180, why not just use the one on the other side, right? So when you have, when you have the cosine only gets you 0 when the theta, the angle is 90 degrees, right? So right, so when you have 90 degrees, you have inner product or dot product to be 0. So in 90 degrees, well, geometrically means two vectors are perpendicular to each other, right? So this concept can be applied to higher dimensions as well, 3, 4, R3, R4, or Rn. So the 2 here is about the perpendicular versus dot product being 0. So V and W are perpendicular to each other if and only if the dot products are 0. The length. Oh, so here is the length of V, right? This is the a number representing the length of vector V. This is the length of W, right? And then we have a we multiply these two lengths together in the denominator. It's not a minus sign. Okay. All right. So the third is about the length of vectors. Okay. So how do we determine the length of the vector, right? You have a vector V, right, representing by this vector joining the point in the origin and the point, let's say V1, V2, Vn. How do we determine the length here, right? You know, in R2 and R3, you can have a visual representation on how do we get the length. So for example, if we have a vector, let's say here, right, you can do it by having break it down into different separate right triangles using Pythagorean theorem. So first you break it down into two into two perpendicular vectors, right? This one is parallel to the z-axis. So this is the same as, well, this vector has the same length as the v, this is x and y and z, right? Has the same length as the z value. So by path, this is, we break it down into the vector here is, let's call it v0, and this is the z vector. Let's use different color. Z vector is here. Okay. So by Pythagorean's law, you get the length of the v square is the same as the the length of v0 square plus z vector square, right? But we know that the length of the z vector is just z, so it's z squared. So what is the length of the v0 vector v0? Well, we can break it down, the vector v0 into here and here. Right. You look at the right triangle here. Right here, in this side, you get vector x, which is the same as which has the same length as the coordinate x. Here you have vector y, which is the same as, or has the same length as the coordinate y. So the length of v0 squared, well, it's just x squared plus y squared. Right? So the result is x squared plus y squared plus z squared. Right? And then this is the square of the length of vector v. So that means the length of vector v is the square root of x squared plus y squared plus z squared. Okay. So in general, for Rn, the length of v is square root of v1 squared, v2 squared, vn squared. Right. If we apply it to Rn, right, n-dimensional vector space, we can imagine what this space look like, what vectors look like, but we can always break it down into separate right triangles and then use Pythagorean laws, right? For, well, first we break it down into the v1, v2 all the way to vn minus 1, and then with the vectors that has the same length of vn, they're perpendicular, and then we separate out. You do the same thing for vn minus 1 all the way to v1 and v2. Right? So that's how we get the formula here. Right? If we notice, what is v1 squared, v2 squared plus vn squared? This is just v1 times v1, v2 times v2, vn times vn. Well, this is another way of writing v dot v. All right. So in general, when you talk about the length of a vector v, it's just you talk about the square root of the dot product with itself. All right. So let's do one example. Let's say you have a vector called 4 minus 1, 2. What is the length? Well, use this formula, you get.
Professor,
Yes.
did you forget to put the square root around the dot product of the two vectors?
You mean here?
In the rest, yes.
Well, notice there's a square here.
Okay.
We're talking about the square root of the length. So now you can get rid of the square root, right? Because
Roger that.
you apply the square root go away, right? So now we don't have since we don't have the square here, we do the square root of the dot products. Okay. This is square root of 4 times 4 plus minus 1 times with itself, and then 2 square, which is square root of 16 plus 1 plus 4, so square root of 21. Right? Does it make sense?
Yes.
Again, as a side note, if you do more generalized vector spaces, and then you have more generalized inner products, right? Basically, inner products beside dot products, other types of inner products. You can always define a length by these dot products. Right? So so the right way of understanding these two concepts is that you have dot product first, and then you can have a derived or induced length from these dot products, right? So when you talk about length of vectors, again, in Rn, the go-to definition of length is the length of this arrow. Right? You can visualize it, but in other, more generalized vector spaces, the length is, may have different shapes or different forms, right? And in other cases, when you have a length, there is no such inner product that you can induce this length from this inner products. So these two inner product and length may not be related. Sometimes a vector space may not even have dot products or inner products to talk about, but they may have length. Okay, and the length have a nice property itself already, right? Even without in the products, is that when you apply a scalar multiple to the vector, and then we talked about the length of this vector as itself, is the same thing as you talk about the length of the vector v, and then we apply this length by the absolute value of the scalar alpha. All right. To see that, you can try to prove it yourself. The proof should be very straightforward. Is that when you do the left hand side is the square root of alpha v dot alpha v. Right? And then we know that the dot product, if we have a scalar multiplication, we can pull out the scalar outside, right? So if we put out alpha here, so we get alpha, and then we can put out this alpha as well. So times alpha, and then multiply v dot v. All right, so this becomes scalar multiple of alpha square times square root of v dot v. So this becomes, right, the square root of alpha square is absolute value of alpha, because alpha may be negative. But when you square it, it becomes positive, and square root of it becomes the absolute value of alpha, right? And here is by definition, is the length of v. So that's how you get this property of length. Right. So the general idea of length is that what if we have, only have properties for length, but and this idea is separated or independent from the dot product. So we don't even need dot product to have such property. But if we have a dot product, this property comes for free, as you can see, right? And another property is that the zero vector, or the vector for the origin, has the length 0, right? Because the coordinate are 0, right? 0, 0, 0 for all n, and when you sum up 0 square is still 0. So the length is 0 by the definition. Okay. And one of the important properties for length are the triangle inequality. Okay, so is that when you have vector v, vector w, when you sum them up, you get v plus w, right? So when you compare the length v and w and v plus w, all right, is that the sum of the length v and the sum of length w is always greater than or equal to the length of v plus w. That you can see that from the picture here, right? This is the parallelogram formed by vector v, vector w, and the sum is the diagonal vector, right? So when you look at the triangle here, right, this edge is vector v itself, right? This edge is the translation of the vector w. We shift the vector up, right? These two are the same vector. And the diagonal is the sum v plus w. This forms a triangle. Because it's a triangle, it has a triangle inequality right away from the elementary geometries in Euclidean spaces, right? When you have a triangle, the size or the sum of the length of any two edges or any two length is always greater than or equal to the third length, right? So this is that's why we call it the triangle inequalities. We can apply this triangle inequality for geometries into lengths of vectors. Okay. Okay. So the last thing we talk about is Cauchy-Short's. How do we how do I spell shorts on this embarrassing? Cauchy-Short inequality. Right. What it says is that when you have dot products or even absolute value of it is always greater than or equal, less than or equal to the length of v times the length of w. Yes, sure. Thank you, Brenna. All right. All right. Why is this the case? Is that when you look back into look back to the angle between two vectors, right? The cosine of this angle theta is v dot w divided by the length of v times the length of w. So you can see that well, when you replace v dot w by that formula is the absolute value of v w times cosine of theta. So equal to, well, let's compare this. And then this is equals to the, well, because these two lengths are always greater than or equal to 0, the lengths are always, non-negative numbers. You can pull this number out of the absolute value with no, penalties, because it's always non-zero, right? Times the absolute value of cosine theta. And as you can see that the cosine theta, the absolute value of cosine theta is always less than or equal to 1. Right, because cosine theta oscillate between -1 and 1. This is a less than or equals to here 1, which is the right hand side here. Okay. So the Cauchy-Short inequality tells us that the dot product, the relationship between the dot product and the length of the vectors, we take the dot product off. In general, this Cauchy-Short inequality applies to any inner product or dot products, as long as the dot product is well defined, right? We have the authentic inner products. The proofs would be sort of, a little bit more complicated when you have generalized inner products. I will go into depth here, but if you are interested in, you can look up the topics here, or we can talk about it in the in other times, like office hour. So now we explore what the dot products can do for us. It can determine the length. It can determine the angle between two vectors. We have triangle inequalities and Cauchy-Short inequalities, and actually the last application, or sort of, I think is the most important application, is the orthogonal projections. Okay, so what is orthogonal projection really? So again, we have a picture of two vectors, right? And the idea of orthogonal projection is to project, let's say, vector v onto the vector w. So basically, we want to have the vector v project to the vector w such that the projection itself, right, lines up with the vector w, and this projection is as, how do I say it, the projection itself would have the least distance from the actual vector itself, right? Sort of like when you have, let's say you have a shadow, right? You want to shadow the vector v to the vector w. So imagine you have a light shooting the vector v, and then you would have a shadow of this vector v on the vector w, right? So if the light is coming this way, the shadow would comes, let's say, so the resulting shadow is here, right? If you change the light in different angles, you change the length of the shadow, right? So if let's say the shadow comes in this way, the shadow becomes here. If the light comes this way, the shadow actually becomes here, right? As you can imagine. What I call it, the projection has the least distance from the vector, is that when it goes from here, right, this point to this endpoint, this is the distance of this projection has to cover, right? And same thing here. When you talk about the projection, the blue projection, this is this dotted line is the distance this projection has to go to cover, right? Go from the endpoints to the endpoint of these projection. So we want to minimize this distance that it travels. All right. So as a an instinct that the shortest distance, right, from that it can travel is going through the perpendicular line. So that's why the red projection is the projection that we want, right? Because this projection, the dotted line here, is actually perpendicular to the vector w. Right? So this red projection is what we call the orthogonal projection. That's the projection we want. And how do we obtain this orthogonal projection? Right? This is a nice projection because the projection basically breaks down the vector v into two components, right? It's a sum of two vectors, right? The vector v naught, which is the projection itself, and the we call it vn, and the vn, which is the vector orthogonal to the vector w. Right. Let's call this. Let's change the names. Sorry. We call it VW. Right. So this part lies in the same direction, or well, the same line as the vector w. So this projection is either pointing along with the direction of the vector w or the opposite of the vector w, because it's a projection. All right. And the vn, right, the other vector, is perpendicular to the vector w. Okay. So since the vn is a normal vector with the vector W, that means that dot product is 0. Okay. So when you apply the dot products of V with W, vector W, right, with the property of dot products, you can distribute the dot products separately. Right. And as you can see that this part is 0. All right. And let's observe this too, right? Because this VW is a projection on the vector W. So they have the same direction, right? So the angle is either 0 if these two are the same direction, or 180 if these two vectors pointed at the opposite directions. So the cosine is always 0. Always 1. If the 0 angle, cosine is 0 is 1. If the angle is 180, the cosine is -1. So the absolute value, sorry, should be absolute value is 1. Right. So that means that the dot product is either is determined by the length of two vectors only. Right. So it's either positive products of these two lengths or negative of these two lengths. But from the Cauchy shorts, what is V dot W? V dot W is V W divided by the cosine theta. This theta is the angle between the vector V and vector W. So is here theta. All right. This is the angle between VW and W. Let's call it cosine omega. To avoid some confusions. Okay. Right. Okay. Yes. Right. Right. So you can see that both the left hand side and right hand side have the length of VW vector W. So the length of VW is just the length of V divided by cosine of theta. Or if you don't want to use the angle of theta, is just V absolute value of the dot product V dot W divided by the length of W. Okay. Right. So this is from the part here. Right. If we ignore the angle theta, right. If we take the absolute value on each side, this is absolute value of V dot W. This is the absolute value of VW dot W, which is only determined by the length of VW and the length of vector W. Right. So the length of VW is just the absolute value of VW, V and W divided by the length of vector W. Okay, so we determined the length of VW, right? So you know the vector is determined by two characteristics: the direction and the length. We know the direction, right? We also know the length because the VW, right? Remember, lies in the same direction as the vector W. So what that means is that VW is just a scalar multiple of the vector W. Right. So what is this scalar multiple to be? Right. So the scalar multiple is determined by the length, right? Because the VW is just a different length of vector vector W. So we just need to make sure that the length of VW has the same length here. So this scalar multiplication is just V dot W divided by W. All right.
Professor, question right there, the vector W at the end, that's multiplication. Like, what's that W vector?
So here is a scalar multiplication of a vector, right?
Yeah, I mean on the other end, all the way on the right.
Right.
Yeah.
So this is a the scalar we that we apply to the W. This is the alpha we want. Right. This is the alpha such that the length of VW has satisfied this condition. This is the length we want this VW to be. Right? Why this is the alpha? Why the alpha has to be this? Is that when you look at the length of VW, is the same as the square root of VW dot VW. Oh, actually, we can use the property absolute value of alpha times the length of vector W. Right? What is well, the absolute value of alpha is V dot W divided by the length of W, right? Multiplied by the length of W. This is cancelled, so we I think I'm making a mistake here. This is actually V. Sorry. Oops. So the absolute value of alpha is V dot W divided by V, the length of V, times length of W.
Professor, can you scroll up to the notes above that yellow highlighted area so I can just take a screenshot?
Give me a second. I think I messed up something.
Professor, can you scroll up a little bit?
Sure. Okay, sorry, I think this is W square. That would make sense. Right? Because in this case, one of the length of W would be cancelled out, and then the result is V dot W divided by W, the length of vector W, and then this and this agree with is consistent. So this is actually okay. So in general, this is the formula of computing the orthogonal projection of V onto W. So this is the of the orthogonal projection of vector V onto vector W. So as you can see that the orthogonal projection of V onto W is different from the projection of W on V. Right? So you have to be careful what is the projection onto. Right? Is it onto W or is it onto V? Right? If it's onto W, that means the projection is aligns with the vector W. We are projecting with the projection is on W, so is on the line of a vector W. If it's onto V, is the opposite. You project the vector onto the vector V. Right? So be careful here, right? Okay. Any questions so far?
Could you scroll up a little bit? I'm kind of confused at the yellow highlighted area. If you can scroll up, how do you, the magnitude of V over cosine theta, how does that turn into V dot W over
Actually,
length?
I think it's a bad idea to throw in the angle parts. Let's leave the angle part alone. Let's just scratch that.
Yeah, because isn't the orthogonal, we're like talking about a specific projection where we eliminate theta altogether. It just results into one.
Yeah. So it doesn't really like has anything to do with theta. It is actually is easier to understand it by the formula here.
Yes, yeah, this is the, yes, okay.
Yeah, because by
Oh,
because
I see.
yeah,
Oh, it
because
makes
these
sense. Yeah.
two have the angles align, so they're either have 0 angle or 180 angle, right? So that means that the dot product is either the product of these two lengths or negative of these two lengths. If it's positive, means that these two vector pointing at the same direction, or -1 if they put it in the opposite, right? So when you do the dot products, is the product of these two with a positive or minus sign. Well, if we put the absolute value, it doesn't really matter, right? The sign doesn't really matter. So that's how this becomes. So when you put the absolute value on each side, right, the equation still holds, right? The equation holds. That means the absolute value of this equation also holds. So if we put the absolute value, it becomes absolute value of V dot W is equals to absolute value of VW dot W, which is the length of VW times the length of W. Okay, so if we put well, if we try to isolate this variable, that means we divide it by each side by the length of W. So that's why we come up with this formula. Is that the length of VW is precisely the absolute value of V dot W divided by the length of vector W. I think this should be easier to
Yeah, it's a
understand.
lot more easier to digest. I was just really confused how you earlier with the cosine, how it simplified to that, but yeah, it makes sense now.
Right. Okay. So that's how we obtain the formula of this orthogonal projection. Okay. All right, so let's do one example, really quick example. Okay. So let's say our V is 1 minus 2, W is minus 1, 1. So what does it look like? This is X and Y plane. Our V is 1 minus 2, so it's right here. And our W is minus 1, 1, so it's right here. The orthogonal projection of, let's say, we project W onto V. So would be a little bit easier to understand, hopefully. So as you can see that the projection is here. Actually, use different color. So this is the projection we talk about. We want to obtain, right? So by the formula, right, the WV, I denote this vector by WV. By this formula is the absolute value of the dot product of W dot V divided by the length of V square times the vector V. So let's calculate this scalar. Right? This is actually, but the scalar is the most important part of this projection, right? Because the V is given. Okay. So what is this scalar really? Is absolute value of the dot product V dot W. Well, what is the dot product? It's 1 times minus 1 plus minus 2 times 1. So it's minus 1 plus minus 2. Okay. So what is the length of V square? Well, this is actually V dot V. What is V dot V? Is 1 times 1 plus minus 2 times minus 2. So 4, which is 5 divided by 5. So minus 1 plus minus 2 is 3. So this is 5 over 3. I mean 3 over 5, sorry. Times vector V, which is 1 minus 2. So this is 3 over 5 minus 6 over 5. Right. Oh, I think yeah, you get rid of the value sign. Sorry. It's minus 3. Yeah, minus 3 over 5, and then 6. This is 6 over 5. All right. Yep. Okay. All right. The sign is accounted for by the sign of the dot products. So if it's negative dot products, that means you have a the projection is going to be the other side, right? Because it's more than 180 degrees, the projection should go to the opposite side. If the dot product is positive, that means there's the two vectors have, it's the projection should go to the same side. So we have a positive dot product. Okay. So the sign is important as well. All right. The last topic I want to talk about is the distance from a point to a line, straight line, of course. So this is your line L, and then this is your the point P. Okay. So as you can see, that the distance from a point to the line represents the segment of the line such that this line is perpendicular to the given line L and also pass the point P. Right? So how do we obtain this distance? Okay, so this distance can be realized using orthogonal projection. Okay, so let's see. Let's say you have the point P, right? And then the origins lies somewhere here. So now you have a vector P, okay, representing by the arrow joining the origin and the point P. Okay, so and then if you picked a point, any point really, any point here, right, you obtain another vector as well. Actually, you don't need that. Switch that. Actually, from a line, remember yesterday we have a parametric equation for a line, right? This is t times vector plus let's say it passed through a certain point x, right? This is how we get the equation for the line. So that means you have a point x and then a certain vector v. So if we translate this vector v, we can have a vector v here. Okay. So that the vector v, right, start from the origin. Okay, so this is the line formed by only vector v. So this is the red line I from yesterday's notes, if you remember. This is the span of vector v. So these two lines are perpendicular. I mean parallel, sorry. All right, and And the idea is to have actually I make it more complicated than necessary. The idea is that you have a point X and a point P, so that this is a vector XP, right? This is P minus X. Okay. And this vector well, it satisfies well, it is from the point P and is also ends at the point in the line, right? But this is not necessarily the distance, right? Because we don't know whether or not this line, this vector XP is perpendicular to the line L. Right? The issue here, XP, not necessarily perpendicular to the line. Okay. So to resolve this issue is to make sure this line will be perpendicular. So that's why we need the orthogonal projection, right? So we draw this. We draw this picture. L is by X and V, and then P here. This is your vector XP. Okay, so the issue here is that this XP may not be perpendicular. So how to make sure it's perpendicular is that if we have an orthogonal projection of this XP to V, all right, then it's separated into two parts, right? The projection itself and the normal vector. Right? So the other one must be perpendicular. Okay, so let's say the projection is V naught, and then the projection, the orthogonal vector is Vn or Pn. So P is equals to V naught plus V Pn. Okay, so actually the Pn is what we want. So Pn is P minus V naught, right? But we already know how to compute the orthogonal projection. The projection is right here. Use this formula. So if we project V on the XP onto V, this is equals to XP dot V0. Sorry, V divided by the length of V squared dot V. Okay. So let's do some real examples.
And Professor, this is another way to do what we essentially covered yesterday, right? So this is like a third way of going from a lot, or like trying to map
No, yesterday, what we talked about is the how do we get the formula of this line L?
okay, and we're just applying it.
Yes,
with
we're
orthogonal.
applying
Okay,
this, right?
okay.
Because from yesterday's material, we know if we have a straight line, you have a associated associating vector, and it has to pass, particular point.
Oh, okay, okay.
Yeah, so it passed the point X. Oops. So pass the point X, and you have the associated vector V, such that the vector V is parallel to this line L. Okay. So this is the formula we have. So we apply this because we need the parallel vector V, and then we need this point X. Right? If we know the point X, we can join the point X and P to form a vector. That's the vector XP. Okay. And then we can project the vector XP onto the vector V by the orthogonal projection. That's how we get the V naught. But V naught is not what we're interested in. We're interested in the orthogonal component. That's the Pn. So we know Pn is just vector P minus V naught. And the V naught is determined by the orthogonal projection. Okay, so for example, if you have a line is let's say T of 2 minus 1 3, and then it pass 0 1 0. Okay, and then we need to find the distance from the point 1 minus 1 minus 1 to this line L. Okay, so first of all, what is the vector XP? Right? The vector joining from the point X to the vector the point P is vector P minus vector X, which is 1 minus 1 minus 1 minus 0 1 0. So this is 1 minus 2 minus 1. Right? Right. And then what is the vector V? Vector V here in this case is 2 minus 1 3. So if we project XP onto V, what we get here is that the V naught is XP dot V divided by the length of V squared. So what is XP dot V? So let's write it down. 2 minus 1 3. Okay, so the dot product is 2 times 1 plus minus 1 times minus 2 plus 3 minus 1, so minus 3, divided by the length of V square, which is 4 plus 1 plus 9. Times V, which is 4 minus 3 is 1 over 14 V. So it's 1 over 14 of 2 minus 1 3. right? So now we have a projection, so we can easily find the normal component, which is P minus XP minus V naught. So this is, well, XP is 1 minus 2 minus 1, so 1, 2 minus 1, minus this component 1/14 of 2 minus 1, 3. This is 1 minus 1/7, 2/14, minus 2, minus 1/14, minus 1, minus 3/14. This is 12/14, minus 29/14, and minus 17/14. So after we find out the vector itself, the length is just square root of 14 square plus minus 29/14 square plus minus 17/14 square. I don't want to do math. Just something over 14. Okay. Yeah. So that's one way of computing the distance from a point to a given line, a point to a line, by orthogonal projection. Okay. Right. So that's everything I want to cover for today. Let's see if a question. Was it X provided? Is it minus? 27? Oh, this is, yes, you're right. Yeah, this is minus 27. Sorry. Yep. Right. The X is provided because from the parametric equation, this is the X, right? Right. So for the exercises in the book, I would post the first set of homework questions after tomorrow's lecture. So you will have the weekend to do it. And then again, the homework is not graded; it's counted as extra credit to the next exam. So you have until the first exam to do the homework problem. So, but the sooner you do it, the more you can I would say more advantage you have as a practice. Yeah. So let's stop this here. Okay, so the notes, yes, I would post the notes in Blackboard as long as as well as the link for the recording. And yeah. But if you want to do some practice in the book, you can look for chapter 2. Good way to practice are the questions. Well, question 1 to 5, actually 1 to 11 are pretty straightforward. Calculate in the product, calculate the length, determine the angle, etc. And question 20 and question 21 ask you to find the orthogonal projections. This should be also pretty straightforward. Okay. More orthogonal projections for question number 24. And okay, yeah. So yeah, you can do these questions and as a practice, ask me if you have any questions or issues doing these problems. Okay. Any other questions? Okay. I guess I will see you everyone tomorrow. All right. Stay safe.
All right, thank you, Professor.
Thank you, brother. Stay safe.
Yes.
Someone asked if you could post the notes, by the way.
Oh
in the
yes.
chat earlier.
I said I will post the notes on.
Okay. All right. Cool.
yeah.
All right. Thank you for the lecture. Take care.
Okay. Okay.